Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, we talked about the different strain components, normal strain and shear strain, and how we can quantify the strain components, that already we have seen, and then we have established a relation between the strain and the displacement, right. And we have seen that for defining the state of strain in plane strain condition, you need 3 strain components, that is epsilon x, epsilon y and gamma xy. Right. Now, pretty similar to your stress discussion, if you recall that if you want to, if you know the state of strain in xy coordinate system, then can you define the state of strain in some arbitrary coordinate system like x prime, y prime. So, that we are going to do, and this is a little bit different than whatever we have, whatever exercise we have done for our stress chapter. Okay. So, now if you look at this figure, so basically this is your xy coordinate system. Now, we are going to define the state of strain in x prime, y prime coordinate system, which is oriented with respect to the angle theta, and that means the angle between the x prime axis and x axis is theta angle. Okay. Now, this is the body, okay, OH GF, this is the body, okay, in say it is oriented in x prime, y prime say coordinate system, and everything is defined, that means all the displacement vectors and your length and all those things are defined in terms of x prime, y prime coordinate system. Though I mean see this is the point O, and this is the point O prime. After deformation it takes the shape O prime, H prime, G prime, F prime. Okay. So, U is the displacement vector along x direction, okay, whereas the same thing if you try to transform in x prime direction, that will be U prime. Similarly, V is the displacement vector along y direction, and that will be mapped or that will be transformed to V prime, okay, in y prime direction. Okay. So, this is basically the transformation. I mean you need to know how to transform the axis. Okay. Well, so other things are defined. Okay. So, similarly I mean the coordinates of point O is nothing but x y. Okay. So, this is your x, this is your x and y, whereas in x prime y prime coordinate system, that is x prime y prime. Okay, fine. So, everything is okay. So, now we are going to write. So, we can write epsilon x prime in terms of the displacement vector in x prime y prime coordinate system, and we know that should be del u prime del x prime. Similarly, epsilon y prime can be written as del v prime del y prime, and we can write gamma x prime y prime is equal to del v prime del x prime plus del u prime del y prime. So, say this is my equation 1. We can write that, because if we know the displacement vectors, okay, in x prime y prime coordinate system, I can define the strain components, okay, normal strain and shear strain in x prime y prime coordinate system. Only thing here we know epsilon x, epsilon y and gamma xy. So, we are going to express these 3 strain components in terms of epsilon x, epsilon y, gamma xy, that means the strain components in xy coordinate system, and at the same time the orientation of the transform or the I mean the new set of axis, okay, will be required. It is very similar to your stress. Only thing is that the the process or the procedure of derivation is different. Okay. Now, by following the chain rule of mathematics, I can simply write epsilon x prime equal to del u prime del x prime, that is given, which is equal to del u prime del x del x prime plus del u prime del y del x prime. Can I write that? Yes, I can write it, right. So, by following the chain rule. Similarly, I can write epsilon y prime is equal to, which is nothing but del v prime del y prime, that is nothing but del v prime del x del y prime plus del v prime del y del y. And finally, I can write gamma x prime y prime is equal to, that is nothing but plus del u prime del x prime. So, that I can write simply in the chain rule system, we can write del v prime del x del x prime plus del v prime del y del x prime plus del u prime del x del y prime plus del u prime del y del y prime. So, all these equations I am calling equation 2. Okay. So, by following the chain rule, I am expressing everything, or my, I mean epsilon x prime, epsilon y prime and gamma x prime y prime by these expressions. Okay. I can express that thing. Okay. So, now from the geometry, we can write so that means we are just basically writing the transformation equation. If you look at the geometry, that means we are going to transform we are going to express x and y coordinate system in terms of x prime y prime coordinate system, and similarly the displacement vectors. Okay. So, we are going to write down those transformation by following the geometry. So, now if you look at the figure, it will be very clear that x can be expressed as x prime cos theta minus y prime sin theta. This is the transformation rule, right, from the geometry. Okay. Similarly, I can write y equal to x prime sin theta plus y prime cos theta. Okay. And similarly, I can write the displacement term u prime is equal to u cos theta plus v sin theta, and v prime equal to minus u sin theta plus v cos theta. So, say equation 3. Okay. So, now substituting equation 3 into first of equation 2. Okay. So, if we substitute the equation 3, whatever expressions we are getting, we are substituting that thing in first of equation 2, that means the expression of epsilon x prime by following the chain rule. So, there if you look at, we can simply write epsilon x prime equal to del u del x cos theta plus del v del x sin theta multiplied by cos theta plus del u del y cos theta plus del v del y sin theta into sin theta. Finally, I can write del u del x cos square theta plus del v del y sin square theta plus del v del x plus del u del y sin theta cos theta. Okay. And finally, we can write epsilon x prime. Now, what is del u del x? That is epsilon x. So, epsilon x cos square theta plus what is del v del y? Epsilon y. So, epsilon y sin square theta plus del v del x plus del u del y is nothing but your gamma xy, right, sin theta cos theta. So, equation 4. In similar way, okay, if we substitute equation 3 in the second and third term of equation 2, then we will be getting the expression for epsilon y prime and gamma x prime y prime in terms of epsilon x, epsilon y, gamma x y. Right, that you can do it by following the similar thing. I mean, very pretty straightforward expression. Okay. Now, if I do the trigonometric calculations, okay, and where the relations are developed based on the double angles, okay, trigonometric relations based on double angles, if we impose here whatever we did for our stress, then we can get the expression of epsilon x prime, epsilon y prime and gamma x prime y prime in this fashion. So, we will be simply getting epsilon x prime is equal to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma x y by 2 sin 2 theta. Similarly, I can write epsilon y prime is equal to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2, which is minus cos 2 theta plus gamma x y by 2 sin 2 theta, okay, and gamma x prime y prime by 2 is equal to minus epsilon x minus epsilon y by 2 sin 2 theta plus gamma x y by 2 cos 2 theta. So, equation 5. Okay. So, these are the equations by which you can get epsilon x prime, epsilon y prime, gamma x prime y prime in terms of epsilon x, epsilon y and gamma x y. right. So, that means if you know the state of strain in xy coordinate system, you can find out the state of strain in any arbitrary set of coordinate system. Okay. If you know epsilon x, epsilon y, gamma xy and theta, if you know, then you can find out, right. So, that you have got from these expressions. Okay. So, we have derived that thing. Now, if you look at this equation, okay. So, equation 5. So, that is pretty similar to the equation whatever we have derived for our stress. Only exception is that here you have half. So, there you had tau xy only, that is the shear stress, but no half was there, right. Here you are getting 1/2 by definition. I mean, when we derived that thing, we got this thing. So, now if you look at this expression, then basically one thing is coming out from this discussion, that we can again construct the graphical representation very similar to the Mohr circle of stress. We are going to we can have Mohr circle of strain if we plot the coordinate system of gamma by 2 versus epsilon. That means normal strain versus half of shear strain. Now, if we plot or if we construct the Mohr circle in this space epsilon versus gamma by 2 space, then basically these 3 equations will give you or will form a kind of Mohr circle. Is that clear? So, that Mohr circle if we look at, so this is the Mohr circle will look like. Okay. So, as I told you, so it is basically epsilon versus gamma by 2 space, and the construction of this Mohr circle is pretty similar whatever we did for stress. So, therefore, I am not going to repeat again the whole process. Only thing is that this is the point x whose coordinates are epsilon x gamma xy by 2. Okay. So, this is given by this. Similarly, you can get point y which is diametrically opposite. So, once you know these 2 points, then basically you can locate the center of the Mohr circle by connecting these 2 points x and y with a straight line. Okay. Then once C is known, you can find out the radius of the Mohr circle and other necessary necessary parameters, and then you can find out the state of strain on x prime y prime coordinate system by just following the same sense of rotation but twice. Okay. So, the angle between x and x prime is theta, but here in the Mohr circle you will be getting twice of theta, that is pretty similar to your stress. So, you are just pointing out the points x prime y prime. Okay. So, the coordinates of x prime y prime epsilon x prime and gamma x prime y prime by 2. Similarly, the coordinates of y prime point is epsilon y prime and gamma x prime y prime by 2. Okay. Now, there are a few things which are pretty similar to your stress. Here also you are getting 2 points, point 1 and point 2, where you have maximum possible normal strain and minimum possible normal strain without any shear strain. So, these normal strains are known as principal strains, and the plane on which they are acting, those planes are known as principal planes. And that also we can prove, though I am not going to prove that thing again. So, that principal stress is associated with principal strain. Okay. So, anyway, so this point 1 will give you the normal major principal strain, and point 2 will give you the minor principal strain. Okay. And that is shown here. So, that rotation, that orientation of the principal axis, okay, is shown in this figure. So, the angle between x point and one point is nothing but twice theta 1, okay, in this mode circle. So, that will be taking only theta 1 in the actual coordinate system, okay. And now very similar to your stress, you are getting 2 points D and E where your normal strain is same, but you are getting maximum possible shear strain, okay. That is your gamma xy is becoming gamma value on those planes will be maximum, right, not gamma xy, gamma value, that is the shear strain will be becoming maximum on these planes. So, and this plane is basically making an angle 90 degree with the principal normal principal strain axis. So, therefore, if you want to draw the axis on which your maximum shear strain is acting, say D and E, so this angle will be 45 degree, okay, pretty similar to your stress. Now, one thing you need to remember, here also we are following the same sign convention, okay, to draw the Mohr circle, whatever we considered in case of stress. Do you remember that? So, we considered that if the normal stress is positive, okay, if the normal stress is tensile in nature, then that will be positive, if it is compressive in nature, that will be negative, right. Here also, if your epsilon x is a elongation in nature, then that will be positive, if epsilon is contraction in nature, then that will be negative, okay. But in case of shear strain, so if your shear strain is positive, then x point will be coming below the epsilon axis. If shear strain is coming negative, then x point will go above epsilon axis, okay. So, that is also pretty similar or in line with whatever sign convention we considered to draw the Mohr circle for stress. The same thing will be continued here also. Now, once you have got the Mohr circle for strain, in case of plane strain condition, we can draw the Mohr circle of strain in case of 3 dimensional or the general state of strain. That is pretty similar. Again, you will be getting 3 different normal strain, 3 different principal strain you will be getting, epsilon 1, epsilon 2 and epsilon 3, okay. So, in case of 3D state of strain, you will be getting 3 different principal strains, okay. And similarly, very similar to your stress, you will be getting the Mohr circle will be like that. So, 3 different Mohr circles you will be getting, and with this combination I can get this kind of Mohr circle, okay. But in all the cases, this figure, here it is wrong. So, basically your state of strain will be always lying in this shaded part, not inside this circle, not inside this circle, not outside this circle. So, it will be always within this shaded part, okay. So, with this basically your stress and strain concept is over. So, you have now you are familiar to the stress as well as strain and how to quantify those things, how to find out those things in some different arbitrary coordinate system, all those things are covered. Now, in the next lecture we will be talking about the measurement of strain using strain rosette, okay. So, there we will see that this Mohr circle, this representation of Mohr circle in the strain plane strain condition or in the 3 dimensional state of strain will be very helpful, very handy to find out the strain in some arbitrary coordinate system by getting the response from the strain rosettes, okay. So, I will stop here today. Thank you very much.